Hello, my name is Brett Haynes, and I am going to be discussing this research paper, Context-Free Attacks Using Keyboard Acoustic Emanations. And at a high level, what this paper is exploring is a way to recover the keystrokes from the audio of a person typing. In this case, what context-free means is that we don't have prior knowledge of where the keyboard is or how it's rotated with respect to the microphones making the recordings. First, let's explore the history of trying to recover messages over telecommunications, and eavesdropping over internet lines, even phone lines and telegraph lines, are as old as those technologies themselves. But more recently, researchers have tried to develop attacks that recover the sound not over the actual line of communication, but using the audio of the message being typed out. For the most part, these attacks have relied on machine learning, which works in some cases, but it has some pretty significant limitations. First, training a machine learning model is not easy. It takes a lot of computer power and a lot of time, not to mention you have to have really high quality data to train the model on. Next, it will generally assume that keys typed one right after the other are related in some way, and for the most part they are. When you type words, you will end up seeing certain pairs of letters coming up. You will see certain letters will follow others with a greater frequency. The problem is that doesn't work for random strings, things like strong passwords, account numbers, anything where the string is essentially random. These machine learning models will fail. And kind of a knock-on effect of that is that when it gets one guess wrong, then it's likely to get subsequent guesses wrong as well, because it's assuming they're related when they're not. So as soon as one goes wrong, there's kind of a knock-on effect where whole swaths of the recording will be just completely wrong. So onto the attack for this paper. The researchers wanted to develop an attack that does not assume the position of the keyboard or its rotation relative to the microphones, and it doesn't assume a relationship between individual keystrokes. That way it overcomes that limitation previously discussed. And how it does this is multiple microphones will detect the sound of a keystroke, and it calculates the difference in time it takes for the sound of the keystroke to reach each microphone, and this is called the time difference of arrival in the paper. And geometrically what happens is, if you have two focus points, and you know that there's a point that is a certain difference of distance away, that gives you a hyperbola. Now that is an infinite shape, so by itself that's not enough information to pin down an individual keystroke. So what this attack does is it adds in more microphones, and more microphones gives you more differences, which gives you more hyperbolas you can stack on top of each other, and that allows you to kind of pin down where exactly the sound would be coming from. Now here are a couple of images kind of showing that idea visually. For each pair, it gives you this hyperbola belt, and the reason there's a belt is because there is some measure of error when recording. These times aren't absolutely exact, so the belt kind of gives the program a little bit of wiggle room to pin down where the sound would be coming from. And then in figure 3 you can see the more belts you have, the more you can pin down the location of the key that the sound came from. So the first question the researchers had to answer was, is this something that is even physically possible? Especially, is it possible with consumer-grade hardware? If you just go off and buy a smartphone off the shelf, will that record with enough fidelity to be able to pinpoint the location of individual keys? Spoiler alert, the answer is yes, but let's look at the numbers. So, pretty standard audio recording goes at 44,100 samples per second, and that is a very long-standing standard in audio recording, so that probably won't change anytime soon. The speed of sound in pretty much any situation is going to be around 343 meters per second. Yes, that is going to be a little bit different depending on things like altitude and humidity, but it won't make enough of a difference to really affect this attack. And finally, the key centers, so that's where the sound actually is emanated from. The center of a key, or of two keys on a keyboard, are typically 19 to 22 millimeters apart. So the question is, does audio sample quickly enough so that each individual sample covers less space than that 19 to 22 millimeters? And yes, if you divide the speed of sound by the number of samples, you get about 7.7 millimeters is how far sound will travel in between each sample. So yes, a regular microphone off a standard smartphone can detect where the keys are. So before we get into the details of the attack, let's kind of look at a broad overview, and this attack really comes in 4 stages. First is a pre-processing step where it takes the recording of the sound of the typing and it cuts it into individual pieces representing each keystroke. Next, it takes those pieces, and for each pair of microphones that is recording, it calculates the TDOA of the keystroke for that pair. Next, it tries to determine how wide the hyperbola mentioned in the last slide should be, and then creates an area that it thinks the key is based on the overlap of the hyperbola formed for each pair used in the last step. Then finally, it uses all of these candidate areas to reconstruct where the keyboard was, and thus where each key was, and then it will match each region to the key it most likely was, where the key it's sitting on top of. So for the pre-processing step, each keystroke is going to make essentially 3 sounds that you could use to kind of pinpoint where in the timeline that keystroke happened. The first is the touch peak, that's where your finger actually comes into contact with the key. Then is the hit peak, that's where kind of the key is fully depressed and it makes that clicky noise. And finally is the release peak, the sound the key makes as you lift your finger and it pops back up into place. And looking at this graph, you can see the hit peak is far and away the most distinctive signal. So that's the one that the algorithm is going to use as a landmark to determine when this keystroke actually happened. And to find those peaks, the algorithm kind of goes through the recording and uses a sliding window of 10 audio samples, and it uses the sum of the energy in those samples to kind of find maximums of where those peaks are. And when a peak is found, the audio is cut into a 100 millisecond section, 10 milliseconds before the peak, 90 milliseconds after it. And that amount was kind of determined by practice, because it was found that 100 milliseconds is more than enough time to record the entirety of the keystroke, but you very rarely had more than one keystroke within the same 100 millisecond block. When recording the time difference of arrival for a signal between microphones, it's easy to think that just using the timestamp would be good enough. Unfortunately, it's just not, thanks to various physical effects and software effects when recording sounds. There can be up to 0.44 milliseconds difference between when a sound actually happens and when the recording thinks it happens. And that's nowhere near good enough. I mean, in that amount of time, sound can travel up to 15 centimeters, which is about half the width of a standard keyboard. So to overcome this limitation, the researchers used a process called cross-correlation. Essentially, you kind of imagine you have the sound wave printed out on 2 pieces of paper. One of them is the reference signal, that one sits still. and the other is a sliding signal. You literally slide it back and forth over the top of the reference signal, and you try to find the offset where the two line up the best, and that gives you like how far apart the audio recordings happened. So when you get kind of the number of samples offset that one recording picked up the sound versus the other, you can convert that into a time offset, which you can then convert into a distance. So here is the full equation for cross-correlation, and I won't go into it for the sake of time, but essentially what it's doing is it kind of calculates both the individual points and the average signal's interference, and the greater the interference is, then the closer those two signals line up. And we're looking for a maximum point for where the signals line up best. So cross-correlation is good, but it can still be a little bit ambiguous. So what the researchers did was generalized cross-correlation. Essentially, you take that same function from the previous slide and you add a weighting function to it, so that way it kind of amplifies stronger correlations over others. That way you don't end up with a few points that look like they might be matches, and instead you end up with one very strong match. And empirically they discovered what's called the phase transform function works well as that weighting function. Essentially it's kind of taken the inverse of a Fourier transform of the strength of the signal. So like I said last time, for each pair of mics, sample offset is converted to time offset, which is converted to distance offset, and we're going to call that distance offset delta D of ij, and we're going to use that in the next slide, so keep that in mind. And then this figure just shows the difference between regular cross-correlation in the light gray line and generalized cross-correlation in the dark gray line, and you'll notice that generalized cross-correlation leads to one single peak that really gives you a good guess for the sampling offset, as opposed to cross-correlation where you've got a few different options. The next step is to try to determine how wide should the hyperbola band be that determines the candidate area. Now, if it's too small, it might accidentally sit or overlap over incorrect keys. But if it's too large, it might be too ambiguous to pinpoint one individual key that it relates to. So the researchers tried to use a relatively conservative error estimate. That way it isn't too big or too small. And what they did was they took all of the measurement errors from a previously done set, and they took the third quantile of distances from that set. And we're going to call that distance W. So the hyperbola is going to be defined by this delta D of ij that we defined in the last slide, and we're going to add and subtract that distance W from it to give us one band. Now, we want to take band for each pair of microphones. So if we have M phones, and they each have two microphones, they usually have one toward the top for recording sound in video, and then they have one toward the bottom for recording sound during phone calls. So if each phone has two mics, then we have 2M choose 2 candidate area bands per keystroke. The final step in this attack is to kind of reconstruct where the keyboard was in relation to the microphones, and thus where each key is and how those keys relate to the candidate bands. So again, this is a context-free attack, meaning we don't know where the keyboard was or how it was positioned relative to the microphones. So what the algorithm does is it takes all of those candidate areas that we calculated in step 3, and it kind of lays them out to determine where are the outer bounds of the area of the keyboard. Now, the more candidate bands, the more keystrokes it uses to reconstruct the keyboard, is better up to a point. They found empirically that the accuracy overall was linear with the number of keystrokes used to reconstruct the area up to about 370. And then after that, the level of accuracy just leveled out. So 370 keys is kind of the magic number to reconstruct the keyboard's area accurately. So to mathematically calculate the position of the keyboard, you want to maximize this function here at the bottom, which takes the keyboard's location R and rotation alpha, and you want to maximize what's called the coverage quality of each candidate area with regards to each key. So essentially you want to set it up so that candidate areas cover one and only one key as well as possible. And when you maximize that for each key, you end up with a positioning where the areas all kind of relate to one individual key each. And that gives you a good way to recover which key each area relates to. Some additional questions the researchers looked at were how many smartphones, and thus how many microphones, should you use in this attack? Logically, more smartphones means more microphones, which means more candidate areas, but eventually you're going to hit a point of diminishing returns, and all of these greater number of areas also means more computation time. So what they found was 3 phones is pretty much optimal. 2 phones is almost always too ambiguous. 4 phones is a little bit more precise, but it also is significantly more complex and thus takes more time to determine. The other big question is, what if the layout of the keyboard is unknown? We are kind of assuming that no matter what keyboard we're listening to, A is in the same spot, B is in the same spot. Specifically, we're assuming it's a standard English QWERTY keyboard. But what if it's not? Unfortunately, that's just beyond the scope of this paper. So after implementing this attack using some standard off-the-shelf Android smartphones, the researchers performed a couple of experiments to see how accurately could this attack recover keystrokes. In the first of these experiments, a couple of volunteers typed out Martin Luther King Jr.'s "I Have a Dream" speech with 3 smartphones recording. And to kind of help avoid issues with special characters or special keys like Control and Alt and Shift, they only used small lowercase letters, space, enter, and delete, which is also backspace because I believe they were using a Mac keyboard. Of note, they never typed the lowercase letter Z, not because anything is wrong with the letter Z, it just happens to not appear in the "I Have a Dream" speech. So over the course of the experiment, each volunteer typed out about 3,400 keys each, and of those keys, the attack accurately recovered 72.2% of the keystrokes in the worst case of the two. Now here we can see some plots that the researchers created of the accuracy of each individual key, in the top left for the letters, bottom left for the special characters. And you'll notice that for the most part, the letters have a roughly equal level of accuracy, which speaks to the relative generality of this attack. Then on the right, it has the accuracy plotted out, so you'll notice that keys which kind of are very large, like space, or stand out on their own toward the edges, they tend to be more accurate, whereas the keys kind of grouped up in the center are a little bit less accurate. They have a little bit more overlap with one another. For the second experiment, the researchers wanted to determine what effect ambient noise would have on the accuracy of the attack. So, to experiment with this, they had volunteers type the phrase "Hello World" 100 times in a row each in 3 different environments. First in a relatively quiet library, then in an open office with some level of activity and ambient noise, and finally in a very busy, very loud meeting room. And what they found was that even in the worst case, which was the meeting room, the accuracy never fell below 64%. So here you can see an actual plot of those results. You'll notice that, like we saw last time, space is the most accurate, but for pretty much all the letters, you'll see that the library had the best results because there was the least amount of noise, thus there's the least amount of errors in the algorithm. And then as noise increased, the level of accuracy fell. So, all said and done, the researchers have successfully created an attack that is viable using standard, off-the-shelf devices and can even perform well in noisy environments. And because the attack doesn't relate the keys to one another, random strings are recognized just as well as standard dictionary words. Unfortunately, it does still have its disadvantages. It doesn't play well with special keys like Shift, Control, Alt, and it still assumes that the attackers know the keyboard's layout beforehand. So that is the end of my presentation on this context-free attacks using keyboard acoustic emanations, and I'm looking forward to answering any questions you might have. Thank you.